All right, so Chapter 6 review is all of the quantum stuff. So it starts with electromagnetic radiation, gets into the Bohr model, goes all the way through Schrodinger's equation and orbitals and electron configuration. So it's kind of a heavy chapter. There's a lot of stuff that goes into that. So I'll give you a quick overview again of all of that stuff. So starting with electromagnetic radiation, we needed to have that understanding of the dual nature of light, the fact that light acts like a wave and also acts like a particle. So we get three equations that come out of that. We get C equals lambda V, E equals HV, and E equals MC squared. So this is all talking about light as a wave, and then it's taking that wave nature of light and turning it into the mass of a particle. That's really what we're doing. So lambda here is our wavelength. Unit-wise, that needs to be in meters. C is the speed of light, which is the 2.998 times 10 to the 8th meters per second. That's written on your periodic table. H is Planck's constant, which is also on your periodic table, which is the 6.626 times 10 to the negative 34 joule seconds. V is your frequency, and your frequency is measured in cycles per second, but we never write cycles, just like the wavelengths in meters per cycle, and we don't write cycles there either. So our frequency ends up being s to the minus 1 power, or 1 over s, or hertz. Those are all values that we can use for frequency. Usually you'll see one of those, though. They don't usually pull out hertz because they don't want to test you on whether you know that a hertz is a cycle per second. And then E is energy. And that energy is in joules. M is our mass, which is the only time in chemistry I'm going to say this. It has to be in kilograms, right? Those of you that have done a lot of physics know that we do masses in kilograms. These are physics equations, so mass will be in kilograms. And then C, again, is the speed of light. And we have to square that. So remember, C squared then ends up being 9 times 10 to the 16th, essentially, meters squared per second squared. All right, so there are the equations. So if it gives you a value for wavelength and it needs you to find the mass, you can just work your way through the equations. Plug in the wavelength, use the constant to solve for the frequency, plug in the frequency, use the constant to solve for the energy, plug in the energy, use the constant to solve for the mass. That's one way you could do it. You also could obviously substitute equations for each other if you have to move through a couple different equations. So you got a couple options there. The real important thing, and I know this year we don't have multiple choice, but the real important thing is to be able to look at these equations very rapidly and determine whether the relationship is direct or inverse. So remember, if your variables are multiplied like they are here and equal to a constant, these are going to be inverse relationships. So as your frequency goes up, your wavelength goes down. And since these are on opposite sides or need to be divided to get equal to a constant, these are going to be directly related. So as your frequency goes up, your energy goes up. And the same here. These are on opposite sides, so they have to be divided to get them on the same side. So they will be a direct relationship too. So the higher the energy is, the higher the mass is. All right, so that's the main part of electromagnetic radiation that you have to be able to pull from this to apply to the rest of the chapter. Obviously, understanding that electromagnetic radiation is light as well as infrared, X-rays, ultraviolet, gamma rays, microwaves, radio waves. It's important to know that all of those things have the same properties. It's important to know that they can move through a vacuum. It's important to know that they all travel at the speed of light. And it's important to know that as you work your way up, your energy is getting higher. and they're getting more and more intense, but also more and more dangerous to you. So radio waves are the lowest, then microwaves, then infrared, then visible light, then ultraviolet, then X-rays, and then gamma rays. And as you keep going past that and your energy keeps going up, eventually you start to get to the more massive particles, the types of radiation that we consider to be particles. You should also know that the colors of light are red on the low end and violet on the high end, and that the conversion from meters to nanometers is 1 meter equals 1 times 10 to the 9th nanometers. So if they had to ask you one of these questions, what they usually do is use a visible light wavelength, which is going to be something in the, let's say 500 nanometer range. So you need to convert that to meters. So just know that whenever you're dealing with visible light, that would be 5 times 10 to the negative 7th meters. You're always going to be in the negative 7th meters with the wavelengths for visible light, right? These would be a wavelength value. And that's what you want to start with. So if you take the nanometers and plug it in, obviously you're going to get the right numbers, but you're going to have all the wrong power of 10. So there's the beginning of chapter 6. And then the important part then is how these equations were used to already predict some things about the atom then that Bohr and Planck were able to, and Rydberg, and a whole bunch of different people were able to calculate ahead of time. So what they knew was that Rutherford's model was wrong, but right. They knew that there was a nucleus. They figured the electrons were orbiting it somehow. They also knew that the classical physics of the time did not explain how those electrons could orbit it, so they started looking at a new type of physics to explain this. So you have the model where you have your nucleus in the middle, and we know that there's a certain attraction for the electrons, and Bohr was working with hydrogen. And so they would excite the electrons, and they would find that the electrons would jump to a higher energy level, and then those electrons would fall back down. And when they fell back down from the excited state, out of that would come electromagnetic radiation. And so based on the amount of radiation that came out, they knew what the difference in energy was between these energy levels exactly. And so then you can calculate then what the different energy levels are that the electron can occupy in the hydrogen atom. And that's what Bohr and Rydberg and Planck did. Now, the significance of the experiment and only seeing the certain bright lines is the recognition that if you only saw certain lines, that meant the electrons could only have certain energies, and that quantized energy states were true and applied. If you saw every color, meaning every wavelength came out, that would mean that the electrons could be anywhere in their orbit. But that's not what we saw, so Bohr's model proved that we had these energy levels and these quantized energy states for the electrons. And since his experiment gave us the bright lines that were predicted based on these energies and using the equations based on the wavelengths, that prediction then was found to be true and proven, and then we moved on from there. So the explanation for why this happened came from de Broglie. Right? De Broglie was the one who said, well, if light wants to act like a wave and a particle, then why can't things that we consider to be particles have wave properties? So he did the same type of experiment that they had done with light, and he did it with electrons, and he found that you got the same results, that electrons interfered with themselves, you got diffraction patterns, you had all these things happen. And so de Broglie was the one that gave us what they call matter waves. And the reason why then the electrons needed to be in these specific orbits was because it had to be a standing wave, where the electron wave met head to tail, right? And since I just did this recently with my chemistry kids, I happen to have a piece of paper here with the wave on it. So a standing wave would not be this situation, because this is a situation where the wave does not match up head to tail, so this would not be an okay energy for electrons to have. But this one, right there, where it does meet perfectly head to tail, and as I spin it around without letting it go, you'll notice that it's complete all the way around. That's what we call a standing wave. And this then would be a possible orbit for the electron. And as you find all the different standing waves, you get all the different possible orbits of the electrons in the atom. And that's how we were able to first reason why quantized energies would make sense. Okay, so now we're past de Broglie. They do have the equation where you have lambda equals h over mv, and that is de Broglie's equation that looks at the wave properties, and you can predict the wavelength from the mass and frequency of the particle that's moving around. So if you knew the mass of the electron and the frequency of the electron, you could figure out the wavelength or vice versa. There you have the matter waves. So Schrödinger then came after that and started to use the idea of the wave properties, but he also had to incorporate Heisenberg's uncertainty principle, which said that we can't actually observe these things correctly because in order to observe them, you have to hit them with energy. And if we hit them with energy, they're going to move. So what that means is the more we know about where they were, the less we know about what they're doing now. Because if we find them by hitting them with light or some sort of energy to say, oh, there it is right there, then it's already moved differently. It's in a different spot. It's moving at a different speed, different radius, whatever. So Heisenberg was saying that no matter what we try to do, we're never going to narrow this down and completely understand everything that's going on in the atom. So Schrödinger took the wave properties, took the probability that Heisenberg provided for him, and came up with a series of equations that started to give us our three-dimensional volumes of space where the electrons could orbit, which are our orbitals. Okay, so our orbitals are our 3D space of probabilities of finding electrons. All right, so the different energies are going to have different spaces, different orbitals, different shaped orbitals. And we know that Pauli came up with the exclusion principle that says we can have a max of 2 electrons in an orbital. And that's because they have to have opposite spins, and there's only 2 spins possible, clockwise, counterclockwise, or magnetic field up, magnetic field down, however you want to view that. So we have these orbitals that can only hold 2 electrons each, and as we add different energies to it, the orbitals get bigger and also change shape. So the bigness should make sense, why they would get bigger. So in the first energy level, the first orbital is our 1s orbital, which we know is spherical. All right, so our electron is going to be somewhere inside this sphere. All right, so this is the first and lowest energy. We know that if we keep adding electrons, after we add 2, we're going to fill this. So if we add a third one, we're going to have to go to the second energy level. And in the second energy level, we get the 2s, which is bigger. Well, why is it bigger? Simple reason is those electrons in the 1s are going to repel the electrons in the 2s, and they're going to force them outside that radius. So the 2s has to be bigger than the 1s. And since the electrons are farther from the nucleus, we have to provide them with more energy so that they hang around. And that's why the 2s is a higher energy than the 1s is. And this is the reason why as you work your way down a column in the periodic table, your radius is getting larger, because as you're working your way down and you're adding more of these energy levels to it, the inner energy levels are pushing the outer energy level electrons away, and that's why your atom keeps getting bigger. We also know that once we get to the second energy level, when we get the energy high enough, we end up with a different shaped orbital. So it doesn't go from 1s, 2s to 3s. We know we end up with 2p electrons. All right, so we get this p shape. And we know that the p shape has 3 different orientations. And so in the p, right, in the s, we can hold 2 electrons. In the p, we can hold 6 electrons because there's 3 different shapes to the p. There's the x direction, the y direction, and the z direction. We know that when we get to the d, there's 10 electrons because there's 5 different shapes. And when we get to the f, there's 14 electrons because there's 7 different shapes. So when you do the electron configurations, you're just kind of following the periodic table and you're adding the electrons into it, and you're following this pattern. And you have to recognize that as you're following the pattern, the S and the P are always going to match the energy level of the row you're in on the periodic table. The D, we know, is always 1 behind, and the F is always 2 behind. And the reason why that happens is because the energy levels are slightly different. And so Aufbau states that electrons are always going to go into the lowest energy orbital, which does not state lowest energy level. It states the easiest one for it to go into. And so when you look at the energies of the different orbitals, we know our 1s is down at the bottom, and then we have the 2s, and then we have the 2p, and then we have the 3s, and then we have the 3p, and then we have the 3d, and then we have the 4s. But what ends up happening is that the 4s actually ends up being a slightly lower energy than the 3d. So the electrons will go into the 4s before the 3d. So if we're going to do the electron configuration for iron, which is 26 electrons, we're going to say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we're at calcium now, and I know that for a couple reasons. One, it's in row 4 in a periodic table, and it's the second one across. Second reason is all these superscript numbers add up to 20, which is what calcium is. So we're at calcium now, and we have to go into the D for the first time. So the D is 1 energy level lower, so it's going to be 3D, and to get to iron's 26 electrons, it's going to be 3D6. All right, so just remember when you get to the D, it's always 1 energy level lower. We also know that we're allowed to use the noble gas form of the electron configurations, so I can easily write argon, and argon takes care of 1s2, 2s2, 2p6, 3s2, 3p6, and then I could just write 4s2, 3d6 after that. Okay, and the last part of the electron configuration then is the orbital notation, which is using Hund's rule. And Hund's rule was the rule that the electrons are going to split between orbitals in the same energy level first before they pair. And so if I was going to write an orbital notation of argon, I would draw 1 representing the 4s orbital, because each of these lines here represents the orbital. Make sure you label it. And I'm going to put the 2 electrons in there. And then I'm going to write my 3d, and I'm going to put my 5 orbitals across. And I'm going to put 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons. So notice I didn't pair it up until each of these orbitals in the 3D already had an electron in it. Then I paired it. So if they ask you how many unpaired electrons there are, you're going to say 4. All right. If the D is full, like zinc, you're full, then you don't write it in the orbital notation. You only have to write the S and the P if the D is full. The only time you have to do the D in the orbital notation is if the D is not completely filled. And then you just continue on from there. If I finished with zinc, I would keep going, and the next thing that would be in the configuration would be 4P, and I'd go on and on and on from there. So that's an overview of Bohr and quantum and electron configurations. That was pretty quick, but you've heard it a couple times now, so we'll just kind of go with that, and we'll answer any questions later.